Hello everyone, in this video I am summarizing the Earth Engine codes from the training conducted from ARSET NASA. If you are not aware of ARSET NASA, ARSET stands for the Applied Remote Sensing Training Program, which trains people about remote sensing. Not only they conduct the trainings, they also share video recordings, presentations, and maybe data after the live presentations. Participants can ask the questions, which is discussed at the end of the training by panels of experts. ARSET NASA can be accessed from appliedsciences.nasa.gov, or the simple Google search as NASA ARSET will lead to the page in no time. The training which I am talking about was conducted in June 2021. It was titled as ARSET using Google Earth Engine for land monitoring applications. The training format was in 3 sessions of 2 hours each. The training taught the participants about the Earth Engine and the ways how it can be used as the Earth Engine tool. I would like to thank, or every remote sensing learner would thank ARSET NASA for this beneficial and valuable training. In this video, I am only going through the course once, summarizing what's in the code. If you want to access the training, everything is there in ARSET NASA's website. So the training was divided into 3 parts. Part 1, Google Earth Engine Basics and General Applications. Part 2, Land Cover Classification and Accuracy Assessment in Google Earth Engine. Part 3, Time Series Analysis and Change Detection in Google Earth Engine. We begin with Part 1. The first line here is the point. So we have already uncommented this. And this point, this variable named point contains a point which has been indicated by ee.geometry.point, which says that these 2 numbers inside the big brackets is the point. The next line here is the importing of the data set, that is Landsat 8, surface reflectance image collection. So this is done by ee.image collection. The string inside the single quotes is the unique string. So if we copy this and search here, we get something like USGS Landsat 8 surface reflectance Tier 1 depreciated. So there has been some changes with the arrangement of the data, but we are keeping as it is for now. The idea is that every data set has the unique string. Next, we want to get the image only from that point we assigned earlier, or we want to get the image that contains that point. This is done by dot filter bounds and our variable name point. We also want to filter it by dates. In this case, image between these 2 dates has been filtered. Of course, this can vary on what we are looking or searching for. Then this has been sorted by the cloud cover. If we looked about the data again, there is a whole list of image properties, and in that list, there is this property called cloud cover. So we are arranging, or we can say sorting, based on the cloud cover. And by ending with dot first, we get the first image with less cloud among all those images from the image collections. So we can print the image by print. So when we run this, we get something in the console, and we get to see more about the image. Bands can also be selected and renamed. That can be done by dot select. So we are selecting 3 bands, and we are renaming it as NIR, red and blue. NDVI, the popular vegetative index, can be calculated like this. The first one here we have selected the bands that are required for the NDVI calculation. And after that, we are doing this directly by writing mathematical operations such as dot subtract, dot divide, dot add. And we are renaming the result as NDVI. Or there is another process. NDVI is the popular vegetation index. So Orphangen knows it. They have this beautiful function just for this purpose. This dot normalized difference with capital D calculates the NDVI after selecting the two bands here. So the results can be displayed as the layer. For that, we can assign some visualization parameters. This is done inside the curly brackets. We have minimum and maximum value, which ranges from -1 and +1. And inside the palettes, we have the colors. And we add the layer with map.addLayer. So M is capital and L is capital. Then we have the variable name. We have the visualization parameters. And inside the single quote, we have the layer's name. So if we run this, we get something like this. There is also another way for that, doing the vegetation index. So this is done by dot expression. So here we have the variable name EVI. And after this variable name image, we have dot expression. And inside the parentheses, we have the formula written inside the single quotes, which is ended by comma. And after that, we have the curly brackets. And inside these curly brackets, we select the bands that are required for the calculation. So we have selected NIR, we have selected red, we have selected blue, and this has been renamed with the capital letters NIR. Similar to above, the result can be added as the layer. The process can be repeated for other indices as well. We have here SAVI, which stands for Soil Adjusted Vegetation Index. So we do this by dot expression again, and we have the formula, and then we select the bands. So this can also be added as the layer with certain visualization parameters. And the line map.center object makes sure that our image is centered in the map here. And the number with this number 9 here is the zoom size. We can also develop the function so to work with the whole image collections, not just for image, and it can be used multiple times. So the function starts with the function. We have here the parameters that is required. Then we select the bands here. We're selecting the band, and we have here the expression for the calculation of the EVI. And here we have dot rename. We are renaming the result as EVI, and we are adding the bands with the image. So we have 3 different bands selected, and we will have the 4th band as EVI. So the EVI will be written as the new band, and this whole function has been named as indices. So this function can be now mapped at the very end. Before that, we are also filtering the data here. We are also filtering the metadata, that is cloud cover length. which is to be less than 20. And we're sorting it by cloud cover. And finally, we are mapping the function. So dot map here applies the function that we developed earlier. Now in the console, if we run this, we see that the EVI band has been added as the new band here. You can see here in the very first image, we only have the 4 elements in the bands. So here we have the EVI added in the list of the bands. So if we further want, we can see what is happening in the maze or what is happening in our vegetative indices. So this concludes the first part of the training. In part two, we have land cover classification and accuracy assessment in Google Earth Engine. We have the dataset here, Landsat 8 image collection assigned to this image, which is filtered or bounded by dot filter bounds with this variable named ccmain. The ccmain is the added save file, and save files like this can be added or uploaded to Earth Engine by this Assets tab, clicking to this new icon. And such shape files are important at the very top here. After that, we have the function. And this function here works on the cloud masking. So clouds are basically masked by working with the QA band. And this works in the pixel level, and the bits 3 and 5 are related to the clouds and its setup. So this function works on those bits, cloud shadow and clouds bits, to mask the clouds. And the very nice thing is that this function can be used multiple times and is helpful for our own purpose. So we have here 2 date filters ranging for some months for the year 2020 and for the year 2019. And we further filter here the dates between these 2 dates, and further from those dates we filter our image, and then we apply the function. So here this maxLSR is the function that we just developed before for masking the clouds. We are applying dot median reducer, and we are clipping our image collection based on our area of interest. And this composite can be added as the layer. So if we run this, we get something here in the layer. And here we have something in the layers now. So something there. And we are selecting this USGS land cover database. If we see here, if we see this data set, and inside the bands here, we have this band called impervious. So this impervious band is related to the percent of the pixel covered by developed impervious surface. So we have the impervious band, and we're selecting this impervious band that has been filtered by date, that has been filter bounds only to be selected from our area of interest. So basically, we are selecting the impervious band here. And finally, we have very short function here in line that just returns the image or the impervious band clipped from our area of interest. So we reduce the image by dot reduce, and then we marks the zero values. We don't want to have the values that are zero in the data. This part 2 of the training was based in a random forest model, the most popular classifier. For this, we require different training points. So this can be drawn from the geometry tools here. So here we have 249 points, and this has been repeated to the other classes as well. For example, water, coniferous, mixed forests, and deciduous. So creating such points is easy. So here we can also see that this feature collection has some property, and that property has been provided with some value. So this has been done to each and every feature collection. And these feature collections has been further morphed as the new feature collection that has been done by dot morph each time. So we also want to select the bands. So here we have the bands from 2 to 7. And we finally create the training data by selecting those bands and assign the regions as the feature collection. And then we are basing the properties from land cover. This is the assigned property to the feature collection, and some scale. And this dot random column here just randomizes them by providing random numbers to them. So we have our random points now. We split our sample points to 80:20 ratio. So 80% of the points will be used for training, and 20% will be used for testing. So this is done by filtering, by filter, inside which we have ee.filter less than and greater than or equal to operators, and we are splitting those random numbers. And we can also count how many points are being used for each cases. So if you run this, so we can count the points by dot aggregate underscore count. So we have the total sample value, and we have number of points for training here, and we have number of points being used for testing here. So random forest is undoubtedly a big topic, but for learners like this, let's understand that random forest is done in orphan by ee.classifier.simple-smile random forest, and inside which we have two different values, 300 and 5. So this 300 here is for the branch, or to simply say there will be 300 different classifications that would continuously run, and each classification would go on and on until there remains 5 predictors in that split branch. So this is how the random forest is going. So after running this once, we can print the confusion matrix and overall accuracy, and also the kappa value. So as to generally define here, this tells us that what pixels were correctly assigned to the given class. So it tells the accuracy about the classification, how the classification went. So similar process is repeated to the testing as well. So we can run this again. So I would say further understandings are required for random forest and to understand what's going on in that classification. So we finally apply the random forest or our classifier to the composites. And here we have the ways to create the legend. So we have here the panel for the legend. We have the legend title for the legend. And we also have the other assigned parameters for the legend. So we are making the row here. We are providing some description here for the label. And we are returning the panel. So if we run this, so this code can be used in our case as well. And we have created palette for the final land cover image. And we add the colors and names. The palette just the for loop to assign each color to the each name. And we add the legend. And finally, we have the palette for our land cover classification. And this is called the SLD style. That is the styled layer descriptor. And this is just a way to visualize the map. So we mark the impervious surface that we assigned earlier. And we finally add the map for the display. So we apply the previous style layer descriptor as .sld style. And we center the map. When we run this, we get something in the layers here. So we have the classification legend here, and we get the land classification. So it might take some time. So basically in the part 2, we have random forest being applied, in which we are selecting the bands from the Landsat 8, and we are also selecting the points. So we have multiple points being used for the classification, and we have here the branches and parameters related to the random forest, and we're applying the random forest. Before that, we have divided our points in 2 different points for the training and testing. So so many things are going in this code. So we also had this ways to apply the legend. I quickly went through them, but this can be viewed in more deeply, in more deep forms, and see how we can use it in our own ways. So overall, and also we had this confusion matrix going on, and we are seeing how the accuracy has done. So I would say this again, that more understanding of these terminologies are required for understanding the random forest. So this concludes the part 2. The third part, or the final part, is time series analysis and change detection in Google Earth Engine. So we import the image collection and is bounded by our area of interest. And our study area has been drawn here, just a polygon. So we have the cloud masking function here, that is mux L8SR, just for masking the clouds. And we have the sequence of year from 2014 to 2020. We have the function applied to, so here we have the function here. Let us uncomment this first. So in this function, we have our start date and we have our end date. And this start date and end date is being selected from this sequence created earlier. And we also have the filter date to be filtered from this image collection, and we're applying the cloud masking function. We are reducing it by dot median, and that image will have the start date as the date for that image. So many things are going within the single function here. And this is the image collection as the yearly composites. So if we run this, we get here images. So we want to calculate the EVI. So for this, we are doing the function here. We have the function here for the EVI. So we are selecting the bands that has been renamed as NIR red and blue. And we have developed the function to calculate the EVI. And this EVI will be added to the list of the bands. And we want to map that EVI to our yearly composites to be resulted as the new band. So we can run this all. And now here inside the features in the image, we have the new band called EVI. And now for the EVI collection, we are selecting only the EVI from those yearly composites. And we are adding the, we are creating the variables, or say different EVIs for the different years. So here we are filtering the dates, and we are clipping by our study area. So this is just the way to get the EVIs from each year. So we have here the EVIs for 2014, 2015, 2016, 17, 18, and 19, and 20. So we are just creating the images. And so you can see here the band here is one of the AVIs. So we are selecting the AVIs for that year. So we can add all the AVI maps as the year. So this can be drawn and we get the list of AVIs added as the year. So we can also add the AVI maps as the in the drive. So for that we have export.image to drive. So we select the image. We can provide some description. We can apply some scales, and we can specify certain pixels. And we can also draw the line chart, and the line chart is drawn by ui.chart.image.series. We select the AVI band. Our region of interest here, ROI, comes from the geometry inputs. And so we have the scale, and we can apply the some text or title for the chart. So when we run this, we get something in the talks because we wanted to export some image, and we get some chart here drawn as 0.1 EDI over time. And we can also do the same thing for the next point, that is RI2. So if we run this again, we have the new chart being drawn. So we can also create the time series GIF of those images. For that, we require this package from this package called Gina for adding the text. So here we have the year names. So year names starts from the 2018 to 2019. And we can create a function. So this function is being created. So this function here is being created to add these year names to the image. And we can print what's been happening here. It's just adding those year names to the image. And finally, we can define our GIF visualization parameters. We can select our area of interest, that is study area. We can select the dimensions. We can have the frames per second and the format of that image. So some properties about where to appear the GIF. And we can add those GIF. And here finally we are adding the text to the image. And we can print the URL of that GIF, or we can directly print the GIF image in the console as well. So the GIF appears here. So here we have the link, and the GIF is being prepared. Similarly, simple image differencing can also be done here. So we are subtracting year 2020 from the year 2014. And this difference can be added as the year with minimum and maximum values, providing some colors and adding this as the layer. So we can calculate the mean value of all those AVIs. And from those AVIs, AVI means we can subtract this AVI from 2020. So this is just a way of calculating or finding the difference between the image layers. So here we have the some way to determine standard anomalies called J-score, and this is done by a simple formula, year minus mean, and dividing by it by standard deviation. So we are calculating here the standard deviation, and we are finding difference between the mean and the year. and those anomalies can also be added as the layer. So if you run them all, we get so many things in the layers. So we can see what is happening in each and every maze, each and every difference. So in that way, we can find the differences between the two times. And maybe there are other complex ways of finding the change detection, but while using the Artisan, maybe simple ways like subtracting or subtracting it from the mean can be helpful in some ways. And we also have the give here being played. So this concludes the part 1, part 2, and part 3. So I tried to basically go through them quickly, and the codes are available. We can check what's going on further, further going to the codes line by line. So if you're watching till the end, I hope this was helpful to you. So I would like to thank ARSET NASA again, and so thank you for watching. Thank you.